in section 4.2, we're going to use what we know about differentiation to talk about something called the mean value theorem. So what we're talking about here, again, in chapter 4, chapter 3 was all about process, learning how to take derivatives. Chapter 4 is about basically what is the derivative good for? What can we use the derivative for so that we can learn things about functions? So in this case, for the mean value theorem, what we're basically looking at is taking a look at a function. So I've got two examples here of functions. One, this looks like a quadratic function, and this one may be a cubic, x to the third power. Okay, and so we're taking a look at functions, and we're taking a look at a domain. So from domain point A to domain point B. And so you have this theorem in your notes, and we're going to annotate these two pictures. So if we look at a domain interval A to B, we'll look at the cubic function first, A to B. So we're looking at this part of the function. And we know this function is continuous. Okay, so that's the first important thing. And it's differentiable, which means it has no corners or cusps. So then what this mean value theorem is saying is that there's at least one point in between A and B. So inside this domain, there's at least one point where the value of the derivative equals the algebra slope using the endpoints. You see, this is rise over run. So this is our function at B minus our function at A. So these two y values and B minus A. So our calculus derivative, in other words, our instantaneous value is equal to our algebra slope. So if we connect the endpoints with a straight line, if we go back to algebra, we can do a rise over run, right? And that's our slope. And so somewhere along the function here, within this domain, there's going to be a tangent line that's parallel to this. So it looks like maybe it would be about here. So at this location, we have this derivative, this tangent line that has the same slope as this. So we kind of pin that location right here on the function, and that correlates to an x value of right here. So and we'll call that value c. So that's really what we're talking about with the mean value theorem. Now, as part of this mean value theorem, there's always the possibility of being at a hill or a valley where our slope is 0. And that's what Rolle's theorem is about. Rolle's theorem is saying, let's take a look at 2 points on a function, a point A and a point B, where we have 0 slope. Okay, so if we took the algebra slope here, there's no rise, there's just a run. So we know this is a horizontal line, it's got no slope. Then, since Rolle's theorem is just basically mean value theorem, we know that somewhere between these two domain endpoints along this function, as long as it's continuous and differentiable at every point, we've got to have a horizontal tangent. And we know back from calculating critical values in section 1 that horizontal tangents means derivatives equal to 0. And when the derivatives equal to 0, we find hills and valleys. So that's that location right there at the top of the hill, or the maximum. So there is that location where our derivative is parallel to our algebra slope. It's the top of the hill, and it's at location C. So that's the summary kind of the mean value theorem. The mean value theorem can only apply over a closed interval. So when we go back up to this description here, notice I have square brackets, square bracket A comma B. Okay, that closed interval gives me endpoints where I can calculate this algebra slope. If we don't have a closed interval, we don't have endpoints. And we need those endpoints for the algebra slope. So just to kind of recap, the mean value theorem says that the derivative, the value of the derivative, somewhere that value equals the value of the algebra slope, somewhere along the domain. So now let's take a look at whether or not functions qualify to have the mean value theorem done on them. For instance, we had this function yesterday, x to the 2/3 power. And so the instructions say that show that the function f equals x to the 2/3 satisfy the mean value theorem on a given interval and find each value that satisfies the equation. So we have to look at between 0 and 1. So 0 is here and 1 is there. Those are the domain points. So if we think about this portion of the curve, it's continuous and there are no cusps and corners until you get to this point. So we can go ahead then and include this point and this point and draw a straight line between them. They're both defined points on the function, and we can calculate this slope. So I'm going to calculate the slope using the endpoints. My first endpoint is at 1, so my function value at 1 happens to be 1. My function value when x is 0 is 0. So this slope is 1 minus 0 over the domain x values, 1 minus 0. So the slope here of this red line is 1. So somewhere along the blue function, I'm going to have a tangent line whose slope is equal to 1. Well, if it's a tangent line, then we're going to find the expression for that tangent line by taking the derivative of this. So, so how do we find out where the slope of the curve between 0 and 1 is equal to 1? The first thing we have to do is find the derivative, and then we can set it equal to 1. So we're going to find that derivative, we're going to set it equal to our algebra slope here. So let's differentiate this. We'll bring down the power. So on this domain, the function is continuous from here to here. Now, we do have a cusp here, but that's okay. As long as we don't have this cusp on the interior, it can be an endpoint, that's okay. But as long as that cusp is not on the interior of the domain, then we can go ahead and use the mean value theorem. If this domain was between -1 and 1, so it was between these 2 points, we couldn't use the mean value theorem because we'd have a cusp on the interior. But as long as it's an endpoint, and as long as it's definable, which it is, we can go ahead and use the mean value theorem. So taking the derivative, bring down the power, reduce the power by 1. So we've got 2 over 3 times the cubed root of x. So that's our calculus derivative, and we're going to set that equal to 1. That was our algebra slope. So I'm going to say that this is 1 over 1 really, and I'm going to cross multiply. So 3 times the cube root of 3 equals 2. And so this is what I have to solve so I can find this location here. So I'm going to divide by 3. I'm going to cube both sides to get rid of this radical. And I'm going to have an x value of 2 cubed is 8 and 3 cubed is 27. So at 8/27ths, so 8/27ths is about a third of the way there, right? That would be 8/24ths. So at 8/27ths, I should be able to graph a point and draw a tangent line with a slope of 1. So there's that tangent line, and notice that tangent line is parallel to the algebra slope, or the slope of this secant line touching the curve in 2 points. So we've got our derivative equal to our algebra slope, and that occurs at this location. And so that's kind of a summary of what I just said. The tangent through the line point 8/27 is parallel to the secant line between 0, 0 and 1, 1. They both have a slope of 1. Okay, so here's a question we kind of covered, but we'll cover again. Can you think of a domain where the mean value theorem or Rolle's theorem cannot be applied on the above function? So any domain where this cusp is on the inside is not going to work. So for instance, -1, 1. If this was the domain, then we would be looking at a cusp on the interior. We could not use the mean value theorem. -1, 2. Same thing. Cusp is still on the interior. -2, 1. Cusp is still on the interior. -2, 2. So all of these domains, you can't use the mean value theorem because of that cusp. And we could go on forever. So any domain that includes x equal to 0, since that's the location of the cusp. And the reason why the mean value theorem can't be used is because at that location of the cusp, we cannot find the derivative. The derivative isn't defined there. So if we can't define a derivative at that location, we can't use the mean value theorem because it includes an expression for the derivative. Okay, so another couple of definitions that we can state and where the derivative, finding the derivative becomes useful is, and we've already kind of started talking about this in section 4.1, is this idea of when a function is increasing and when a function is decreasing. And so if you remember back to our discussion in 4.1, increasing functions had positive derivatives, right? That's when the value was going up, and decreasing functions has negative derivatives. And so we can look at this both from a function standpoint, that's this top box, and from a derivative standpoint, that's the bottom box. So if f increases, if the function gets bigger on the domain, that means the early function value is little and the later function value is bigger. That's an increasing function, right? Function value is getting bigger. Number 2 says the function is decreasing on the domain if our early functions are the big numbers and our later function values are the little numbers. So as the values get smaller, the function is decreasing. So kind of intuitive there. We've already talked about the derivative in section 4.1. If the derivative is positive, then we have an increasing function. We have values getting bigger. If the derivative is negative, we have decreasing functions. The values are getting smaller. So those are just kind of stating 2 things that we've already been talking about. So let's take a look at this. We have some kind of obvious definitions. So a function is increasing over an interval if the derivative is always positive. So here's a location where the derivative is positive. So all of that indicates then we have an increasing function in that location. And then if we look here, here's another area where the derivative is positive, so we have an increasing function in that location as well. So all increasing means that the function is going up. So the function is going up here, and the function is going up here. And then in this center location here, we have a decreasing function. So we have a negative derivative here. And we can see that our function values are getting smaller. So really all of these definitions, though, are to be able to work with functions when we don't have a picture. So we're going to use finding the derivative and looking at the sign, just like we were doing when we were making our derivative number lines. And from that number line, we can say whether or not the function's increasing or decreasing. So first step we need to do is to find that derivative and look at where it's positive and look at where it's negative. So here's our derivative, 3x squared minus 3. Now, if I want to know where it's positive or negative, really, the useful thing is to find out where it's 0. Remember our critical points. That was our, basically our first step in our extrema strategy. So we're going to go ahead and find those critical points. We're going to set the derivative equal to 0, and then we're going to solve this. So we're going to factor out a 3, and I divided it. I factored out the 3 and divided it, so I'm left with x squared minus 1. I'm going to go ahead and factor that to x plus 1, x minus 1, and then I'm going to set each one of these equal to 0, and I'm going to solve. And when I do that, this is equal to negative 1, and when I do that here, it's going to be equal to positive 1. So I'm setting up my number line. My critical points, my derivative is 0 at negative 1 and positive 1. So now I have to look along that line at other values. So we know that the derivative is 0 at negative 1 and 1. So those are our critical points. So I put them over there on my derivative number line. The critical points occur when x is equal to negative 1 and x is equal to 1. Those critical points have 0 for the derivative. Okay, so now if we want to know where the function is increasing and decreasing, we want to look at the sign of the derivative. So we're actually going to skip around here a little bit through our steps that we were using in section 4.1. So we're going to actually skip to step 3 here. We're going to find the value of the derivative between the critical points, because we really want those pluses and minuses, so we can see if it's increasing or decreasing. So we're going to look at the derivative. And let's pick a point over on this side of the first critical point. So let's pick x equals negative 2. And when I plug in negative 2 here, I square it. I'm going to get 4 times 3 is 12 minus 3. So that gets me 9. So it's a positive number. So that means I know I have a positive derivative in this region. So I have an increasing function. Let's take a look at between. the critical points. So I'll choose 0. I put 0 in. So square 0, get 0 times 3, still 0. Subtract 3 is negative 3. That's a negative number, so I know between the critical points here, I have a negative derivative, so I must have a decreasing function there. And then on the other side of the critical point, I'll pick 2 again. And so 2 squared is 4, times 3 is 12, minus 3 is 9. It's a positive number, so I must have an increasing function over here beyond the critical point on the right. Okay, so I have increasing, so my function's going up, then my function goes down, then my function goes up again. So the function's increasing on this domain from -1 all the way out this way. Notice that I'm not restricting this function at all. I don't have any domains. It's just all real numbers I want to use. In section 4.1, we were restricting the domain and having to check endpoints. We don't need to check endpoints here because we have no endpoints. So if it's positive over here, if this derivative at -2 is positive, which it is, it was 9, then it's going to be positive forever because there's no other critical points. So all the way into negative infinity, that should be a negative. So negative infinity to -1. It's also increasing over here from 1 to positive infinity. So this is a typo. Remember, it's a typo. It should be negative infinity. And then the function is decreasing here between these 2 points. So from -1 to 1. Notice when I use this interval notation, I've got open-end brackets. Okay? We don't worry about what's happening at the critical points. We just want to know what's happening on either side and between the critical points. So as we can then look a little more critically, not to be punny, but at this function, let's try to sketch it. So we know the derivative is 0 at x equals 1 and x equals -1. So if you notice I'm jumping around, I'm jumping back to step 2 now. Let's find our function values. Okay, so at -1, if I go back to my function, x cubed minus 3x, I plug in -1, I get -1 plus 3, right? -3 times -1, that's 2. So my function value is 2 at this critical point here. Let's go ahead and find our function value at this critical point. So that's when x is equal to 1, so I plug 1 in here. When I do the math, I get -2. So my y value here is -2. So now I have my critical points, and I know how my function is behaving as we approach this critical point. It's increasing, and then I know how my function is behaving between the critical points. It's decreasing, and then I know how my function is behaving on this end. It's increasing. So we can go ahead and sketch a smooth curve between those critical points, connecting those critical points. So the function should look something like that. So let's talk a little bit more about when the derivative is 0. Okay, so if we think about this, a derivative equal to 0 means a slope of 0. It means a horizontal line. So we say if the derivative is 0 at each point of an interval, then there is a constant c for which the real function is just the value c. So in other words, if I want to draw a function with a derivative of 0, I'm going to draw a horizontal line. So let's give us a couple examples here. For instance, here's a horizontal line, f of x equals 2 or y equals 2. That has 0 slope. So it has a derivative that's 0. If I ask you to take the derivative of this, the derivative would be 0. G is equal to g of x is equal to -3. Again, horizontal line. It has a 0 slope. And if I took the derivative of this, you'd say it would be 0. Here's another one. H of x equals pi. Pi is 3.14. That's still just a number. So I draw a horizontal line at 3.14, just a little bit above 3. If I took the derivative of this function, you would say it's 0, and you can see that this function itself has 0 slope. So what we're saying is that if I have a constant function, it's going to have 0 slope. So we can say the reverse is true then. If I have 0 slope, I must have a constant function. Okay? So let's talk about then when the derivatives are the same. does it mean the function is the same? So let's have a couple of examples here. For instance, let's have a derivative of 3x squared minus 6x. Could you find a function? So this is already a derivative, and this is already a derivative. That's why we have the derivative here. So think of something that would yield 3x squared as a derivative, and think of something that would yield negative 6x as a derivative. So let's think about this. The power rule, we know the power rule is to bring the power down and reduce it by 1. So this must have been the original power. So then the original function here must be x cubed. So let's kind of back check this. If I take the derivative of x cubed, I get 3x squared. And this negative 6x, we see that this x has a power of 1. But this is the derivative, so the original function must have had a power of 2. So if the original function must have a power of 2, then I have to kind of modify this constant out here so that when I take the derivative, I get my 6. So 3x squared has the derivative negative 6x, or negative 3x squared has the derivative negative 6x. So there's a possible function, and it looks like this. That's what x cubed minus 3x squared looks like. Is this the only function that has this derivative? So think about that for a second. Or are there other functions that would yield the same derivative? Could you think of something, a function, now that you know how to kind of get this and how to kind of get this? Is there any other function that would still end up having this as the derivative? So that's kind of what we're looking at. So if you think about that, and our last screen about the derivative of constants being 0, then you could maybe guess that if I just throw a constant on the end, then when I take the derivative of this, I still get this, because when I take the derivative of 1, it'll be 0. And so if we can do that again with a different constant, for instance, this, again, it's a different constant, but when I take the derivative of this, I'll get 3x squared, which is my derivative, minus 6x, which is the other part of my derivative, plus 0, because the derivative of a constant is 0. So g of x is this red curve, h of x is this green curve. If you notice, the functions that all have the same derivative are just offset vertically. Then they're offset by this constant. The blue function was at 0, 0, because it had a constant of 0. This constant of 1 bumped it up 1 to the red function, and this constant of 3 took the blue function and bumped it up 3 to the green function. So functions that are off by a constant will have the same derivative. So that leads to this general expression here that was up here, but I wrote it again down here. Our function g of x is basically our function f of x with a constant thrown on the end. So if you can see that right here, g of x, here's f of x, here's g of x, and I see f of x right here with a constant on the end. And all of those will have the same derivative. H of x, same thing. It's got f of x with a constant, a different constant, but same sort of general principle there. So functions with the same derivative differ only by a constant. This has a constant of 0, this has a constant of 1, and this has a constant of 3. So let's try this example. Find the function, and I'm calling this big F of x. So the fact that this is capitalized is really significant. We're going to find a function, let's call it big F, whose derivative is sine of x, and whose graph passes through 0, 2. So think about what function could we take the derivative of to get sine of x. Okay? So we know that the derivative of cosine is negative sine. That's close. I want just sine. That being the case, if we take the derivative of negative cosine, we should get positive sine. So this function, big F, must be negative cosine of x. But is it just that, or does it have some constant on the end? So we know big F of x could be just negative cosine, or it could vary by some constant. So what we do then is we say this, big F of x is negative. We know for sure we need our negative cosine, because when we take the derivative, we get sine. But we could have some other number out here. And the only reason we can, or the only way we can find this number is to know this information, that when x is 0, big F of x is 2. And so we're going to put 0 in for here, and we're going to put 2 in for here, and we're going to find that c. So cosine of 0 is 1. So we end up having 2 equals -1 plus c. Okay, so when I solve this algebraically, add 1 to both sides, I get a c of equal to 3. So that means I must have a 3 out here. If I have a 3 out here, then I can pass through this point 0, 2 right there. So let's go ahead and graph this. So when cosine of x is 0, we have a value of 1. And so this is really my cosine curve. You know, cosine, it's really my cosine curve that's flipped, and then it's shifted up 3. So it looks something like this. So at this point, you can start the homework for day 1. And day 2, we'll talk a little bit more about finding that function, big F of x. So we'll talk a little bit about that, and then we'll do also some anchor charts for mean value theorem and critical points.